Welcome to this fourth lecture in the Structural Dynamics course. Today we're going to consider, of course all topics are important, but we're going to consider an important topic. That is the question of damping in structures. So in many real life structures it's actually quite easy and straightforward to calculate the mass. It is also fairly simple to estimate the stiffness either by computer models, analytical solutions, or by measurements where you estimate the frequency. But the damping, that's actually a quite unknown quantity, and in most cases it's actually included in models that are formulated in terms of mathematical convenience rather than to replicate correct damping behavior in structures. So one particular case we've considered is, of course, resonance, where we have a build-up of resonance until we reach a steady state where we have a constant amplitude and a frequency that a period that is determined by the natural frequency, the resonance frequency of the structure, and we have displacement along the vertical axis and time along the horizontal axis. And this we could then transform into an frequency response solution where we have the displacement over the static displacement, and if this is normalized to unity, then the peak value will be 1 divided by 2 zeta. So that means that the amplitude is 1 divided by 2 zeta times the static amplitude that we've obtained in the low frequency limit. And here you see that the amplitude is inversely proportional to the damping ratio. So the damping ratio is crucial in estimating the amplitude of the structure and thereby determining fatigue of a lifetime of a structure, the collapse analysis of structures. Many things are actually directly governed by the damping properties in a structure, and thereby it is highly critical that we have good damping models to be used in real life analysis. And that's a main drawback of today's state-of-the-art in dynamic analysis, and something I think we should improve. So lecture number 4 on damping mechanisms. We will initially have a look on a general property of damping, namely the question of dissipation of energy. So we want our damping mechanism to extract energy from the system, and thereby for free vibrations to impose a reduction in the amplitude as function of time, and for harmonic excitation at resonance we would like to obtain a steady state amplitude level. Both of them is simply governed by the fact that damping should dissipate energy from the system. So the dissipation is conveniently expressed in terms of an energy loss factor, commonly just referred to as the loss factor. And this loss factor can be obtained for many different types of damping models. It can even be estimated from experimental results. So from this loss factor, we would like to obtain an equivalent viscous damping model. The reason for that is that all our analytical results, even for free vibrations, for forced vibrations, all depend on us having a viscous model. So out of convenience, it's a good idea to transform your general damping model, maybe even your loss factor obtained by experiments in the lab. You convert that into a viscous damping coefficient, and we will refer to that as the so-called equivalent viscous damping coefficient. And the remaining 3 bullets, or the following 3 bullets, all consider different types of non-viscous damping models based on friction, based on hysteresis, or damping, structural damping that is frequency independent, also referred to as hysteretic damping, not hysteric damping, hysteretic damping. And finally, let's have a look at a fluid damping model just to finalize kind of the different possibilities you'll find in reality, in real life, for damping, namely friction, hysteresis, and fluid type damping. And at the end, we'll have a look at some typical values for damping, and the common denominator for these different values are that they are generally small. So structures that are prone to dynamic excitation, that are sensitive to dynamic excitation, typically are quite lightly damped and have relatively small damping ratios. Let's have a look at the dissipation condition. So let's just draw a single degree of freedom structure. It is composed of our by now well-known block of mass m, and it is suspended to the ground by our spring stiffness k. And typically now I would, in parallel with the spring, draw a viscous dashpot. But instead, let's put in some kind of generic device. Box could be a piston inside a cylinder, could be some electromagnetic device that somehow operates like an extra element, internal force. And let's assume that this device here contains some kind of forcing function. It could be function of displacement or velocity, and it will enter on the left-hand side of our equation of motion next to, of course, the inertia that determines our degree of freedom and the restoring force from the spring. So this general function h is now considered as a function that will somehow introduce damping. And the corresponding damping force we will then consider as minus h, which means that the corresponding damping force is considered as an external force that will then operate and provide dissipation of energy. But it is simply moved from the right-hand side of the equation of motion so that it appears where we would expect the viscous damping term to appear. But in general, it just represents damping, and we are going to consider different types of these damping functions h. We would like to associate damping with the dissipation of energy. Therefore, it is convenient to transform our force equation of motion for 1 into an energy-based equation of motion. And we do that by multiplying on both sides with velocity. And then we recognize that the derivative of kinetic energy will be mass times acceleration times velocity, while the differentiation of elastic energy provides us with k times displacement times velocity. That means that the time derivative of mechanical energy that we have within the parenthesis accounts for the first and the third term on the left-hand side in 4.2. That means what we have left is the damping function, the intermediate term. And this is then moved to the right-hand side of the equation, where it appears as an external contribution to the rate of work. So this equation tells us, once we've realized that kinetic energy is 1/2 m velocity squared, elastic energy is 1/2 stiffness displacement squared, is that on the left-hand side we have the rate of mechanical energy, and our equation of motion tells us that that is equal to the rate of work, external work provided by the external loading, minus the dissipation of energy by the damping function. So the right-hand side is the difference in work produced by external loading and dissipation of energy. Now, at this point, it could be of convenience to just recapture what happened during steady state. During steady state, we have a build-up. This is something that looks like resonance with a nice linear build-up of the amplitude. And then at some point, we will actually have what appears as a constant amplitude. And the reason why we get a constant amplitude is that the terms on the right-hand side of this energy balance equation, they will actually cancel. And if we dissipate the same amount of work that we put into the structure by the external load, then we will have that the rate of change of mechanical energy will become 0, and thereby the amplitude will be constant, because mechanical energy is, as we know, another form of amplitude. So it represents amplitude. Actually, the square root of mechanical energy is related to what we consider as amplitude in a time simulation. So that simply means that steady state corresponds to cancelling of external work and dissipation of energy. Now, for us actually to be able to dissipate energy, on the right-hand side, the h times velocity must be larger than 0. And this is actually a condition that must be fulfilled at any times. If it's not fulfilled, that means that your damping device, could be a fluid damper, could be friction, could be whatever mechanism, will actually put energy into our system. And that is not in agreement with the device to be reactive. That requires external powering. So if your damping device does not dissipate energy for all time. It will actually add energy, and that requires an external source, power source, and what we will refer to as active control. And we're not going to consider that in this course. So we will, for all our damper models, always consider this quite important dissipation condition that should be fulfilled for the damping models that we consider. Our premium damping model is, of course, the viscous damping model. The viscous damping model is obtained by H being equal to C times velocity. And if we take this H value for the viscous damper and stick in to our right-hand side or back into our condition, then we see that the dissipation condition H times X dot gives us C times X dot squared, and this is larger for 0 when, of course, C is positive, or at least non-negative. So not only is our viscous damping device mathematically convenient because we can get analytical solutions for most of our problems, but actually it also directly and very easily satisfies the dissipation condition. How can we now actually assess damping? What is large damping? What is small damping? Damping is, of course, relative compared to the size of the structure and the other forces acting on basically our mass m. And one way to do that is to introduce a so-called energy loss factor. So let's just have a look at the equation of motion, where we on the left-hand side will have inertia and stiffness, and on the right-hand side we will have our damping force. So this is actually for free vibrations in its current form, or at least we do not directly include the external loading. Now again, we transform our equation of motion into an energy balance equation. We multiply by velocity, and by now we know that on the left-hand side, the two terms will transform into kinetic and elastic energy, or the rate of mechanical energy, and on the right-hand side we'll have damping force times velocity. Now, this equation in 4.8 is actually energy per unit time. And that means to actually get an estimate of the actual energy that is converted in our system, we should actually integrate equation 4.8. So we apply an integral on both sides. And on the left-hand side, when we integrate the rate of mechanical energy, we will actually obtain what we refer to as the change in energy. And this change in energy can be evaluated by the right-hand side of 4.8. So if we have a look at that, we apply an integral, and inside the integral we will have Fd times the velocity. Furthermore, we assume a minus in front of Fd because the Fd is moved to the left-hand side because we want to consider the dissipation of energy in terms of an internal force. So this is just a question of how we're going to define our loading, our damping force. Is it an external force working on the structure, or is it an internal mechanism that dissipates energy? And it is the latter that is commonly considered. We will now actually consider a particular case, and that is the case where we function of time and we have x along here. We will consider the case where we have constant amplitude. So we will have a particular amplitude. Let's refer to that as capital X, and we could put that down here. We will have a constant period that is equal to 2 pi divided by omega. And we will go even further and probably assume that we will integrate, because we are in free vibrations, we will integrate over the natural period of our structure. That means we have 2 pi divided by omega 0. So the integral that we apply in equation 4.8 is actually an integral over the period that is then carried out. Now let's consider a period in the upper right drawing. So we could start out at a maximum point, then we integrate along this path down to a minimum, and again back to a maximum, and these two maxima have the same value because we are in a steady state or an assumed constant amplitude situation. If we then make another plot, as shown in the figure to the left, we will, along the x horizontal axis, put the displacement, and along the vertical axis, we will instead draw the damping force. Then we will actually integrate from the maximum point, and then we'll move down to the minimum point and increase x again until we reach the same amplitude point. So if we put a cross at the minimum, we are at the minimum here, and the two bullets in the upper right figure are both associated with the maximum point in this displacement force curve. And such a drawing represents a so-called hysteresis cycle. And if we were to draw more periods, then we would simply see lines lying entirely on top of each other. This would be the subsequent period. So therefore it makes good reason to only consider a single period. So an integration where you start out at one point and you end up at the same point can be written as a so-called circular integral or path integral, a closed path integral, meaning that the evaluation of the integral actually corresponds to ft times displacement. And ft times dx corresponds to the area inside the hysteresis loop. And if we move around the entire loop, we will simply integrate ft times dx. And ft times dx is the same as energy. So force times displacement is our work, and thereby referred to as energy because it's an internal force. So from that we see, from this argument, we obtain that the area inside the hysteresis loop that we generate over a single vibration period when we plot the damping force as function of the displacement gives us the dissipated energy per period. And that's a measure for damping. So if we increase the damping, we will increase the area underneath or within the hysteresis curve, and that will increase the amount of energy that we dissipate by our damping mechanism. Now the change in energy has dimension of joule, and a certain amount of joule is difficult to assess as either being small or large. It all depends on the other forces acting on the structure. So therefore we introduce a relative measure of the dissipated energy, and this relative measure is referred to as the loss factor. So we divide the dissipated energy per cycle or per period with the maximum amount of energy available in the structure. And this maximum energy is assessed by the corresponding elastic energy. So at maximum deflection, we will, if we consider a linear stiffness K, we will have accumulated a certain amount of elastic energy expressed as the area underneath the triangle, assuming linear elasticity, and that gives us 1/2 times K times X squared. And that simply means that this value here is K times capital X from the stiffness. So any stiffness contribution to our function H, or the damping force Fd, will be represented by an inclination of our hysteresis loop. And this generates the corresponding maximum elastic energy that we will use to normalize our dissipated energy to give us the so-called loss factor. And since the loss factor is introduced over a period, it turns out to be convenient to furthermore divide the dissipated energy by 2 pi. That means for typical damping models we have much nicer results, and also the loss factor becomes easily related to our damping ratio, as I will show in a moment. So the loss factor assumes constant amplitude. This you can generate in the lab by putting your material inside some kind of straining machine, and then you oscillate your material at a constant amplitude and a constant frequency. Then you obtain hysteresis loops, such as the one shown to the left on this slide, and you find the area and you stick that into the expression for the loss factor, and then you have a measure for the energy dissipation of your particular material. Let's have a look how the loss factor and the behavior of classic viscous damping can be assessed. So first of all, the easiest way to simply introduce harmonic motion is to assume harmonic motion. So we write up x as with an amplitude capital X, and we assume the cosine omega t to be the temporal function. So omega here gives us the corresponding period as 2 pi divided by omega. We also need the velocity, so we time differentiate displacement, and we get minus omega x, and the cosine will then become a sine function. Now remember that Fd is an external force. So let's assume that the element we are going to consider is a typical internal material model where we have a spring in parallel with a viscous dashpot, and we will then have the displacement amplitude x across this element, and the forcing will then simply be minus Fd. That means that Fd is equal to minus kx minus cx dot. So we substitute in the expression for kx and the expression for cx dot, and then we consider that capital X cosine is simply x. Well, of course, sine squared is equal to 1 minus cosine squared, and that means that sine function is the same as the square root of 1 minus cosine squared. If I multiply by capital X, I will get capital X squared, but then I'll also get capital X times cosine squared, and that is the same as x squared. So this means that what is actually written here is capital X sine. And remember, whenever you take a square root, of course, you will have a plus minus, and that's what is given in this expression here. So for a classic, what is referred to as a Kelvin type, also Vogt sometimes, element where you have the spring and the dashpot in parallel, which represents typical material behavior with stiffness and damping, then it turns out that you will actually get an ellipse. Because if you take the stiffness term and move to the left-hand side of your equation, and you take the square on both sides, you will get an expression as given on the bottom of this slide, which actually turns out to be the mathematical formula for an ellipse. So if we plot the damping term, damping force, along the vertical axis and the displacement along the horizontal axis, we'll have that the first term will actually provide an inclination of our ellipse, with the inclination given by the stiffness. So if you only have a pure viscous damper model, you will not have an inclined ellipse, but you will actually have an ellipse that is horizontal. Then you will have the x coordinate expressed in terms of capital X. That means that the maximum deflection in the positive and negative domain will be capital X, and we will have that the crossing of the vertical axis directly determines the damping force, amplitude of the damping force, given as c times omega times the amplitude x. And then we will have an elliptical behavior or shape of our hysteresis loop for pure viscous damping. And for other damping models, we will of course have non-elliptical behavior as you've seen previously on a slide. And the question is, of course, how will this hysteresis look when we have friction, when we have fluid damping, and other types of damping mechanisms. The main idea of today is to convert other damping models into an equivalent viscous damping model. So to prepare this, we need to figure out what is actually the loss factor for a viscous damper. And the idea was, of course, that the energy or the area inside this hysteresis loop is equal to the dissipated energy per period. So we assume again harmonic motion here with a cosine. We time differentiated it to get a sine function for the velocity, and in our case now we will only consider a damping force that contains the viscous term. So we neglect the stiffness term in the damping function. And that means that our damping force will be minus c omega capital X and a harmonic sine function. So we defined the loss of energy as a integral over a period, velocity times Fd integrated over time. We did the transformation into a contour integral simply to identify that the dissipated energy is equal to the area inside the curve. Sometimes it's quite easy to estimate the area inside a hysteresis loop. In other cases like this, where we have a nice mathematical formula for our damping force, it's easier to evaluate the dissipated energy directly by mathematics and solving the integral. So we will do the integral, and then we will have c, and then we will have x dot squared dt. We will then substitute in our expression for velocity, and it turns out we will have c as a constant, independent of time. We will also have omega capital X that is independent of time, and what we are left with is an integral over a period that is equal to sine squared omega t dt. And then we remember that the period is just a time integral, or represents the domain from one time instant to the next time instant that is advanced by a single period. So we could start out at 0 and end up at a period that is equal to 2 pi divided by omega sine squared omega t dt c omega x capital squared. And this is actually the integral that we have right here. One way to solve this is to identify that the argument inside the sine function is not t, but it's omega t. And that means that we multiply by omega, but we also divide by omega, and that means we only have omega and not omega squared, as we have in the previous expression. And suddenly we are not integrating from 0 to a period, but we are integrating from 0 to 2 pi. And this you can look up in any mathematical textbook or try to solve on your computer, and you'll find out that it's equal to pi. In many cases, when you need to look up solutions, mathematical solutions, it's always a good idea to make your integral non-dimensional with the same integration variable as the variable inside your oscillatory function. And that also gives you non-dimensional integral limits. So therefore, the dissipation of energy is equal to pi omega times the viscous parameter c times the amplitude of your assumed harmonic motion capital X squared. Then remember that the loss factor is equal to the dissipated energy that we know by now, divided by 2 pi and divided by 1/2 k capital X. So this introduces some kind of structural stiffness that you are supposed to know if you want to evaluate or determine the loss factor. So the loss factor we determine by this expression here, and we see that terms cancel. So the pi cancels here, value 2 cancels with the 1/2, and we actually have that x squared cancels in both numerator and denominator. Thereby we end up with a very simple expression for the loss factor in terms of viscous damping. That is the angular frequency by which you oscillate your material or your damping device. Then it is the viscous damping coefficient divided by the stiffness. And this is a non-dimensional factor. Now remember that your viscous coefficient divided by your oscillatory mass is equal to 2 zeta omega 0. So that means that C can be replaced by the damping ratio zeta by the relation 2 zeta omega squared m, and that is equal to 2 zeta, and that will actually then be equal to the square root of km. If you use this expression and you substitute in for C, then you'll have an expression for your loss factor that is equal to omega divided by k 2 zeta square root km, and that gives us 2 times the damping ratio. We have omega, and we have the square root of m divided by k. And this one is 1 divided by the natural frequency omega 0, so we get 2 zeta. The angular frequency omega by which you oscillate your damping device divided by the natural frequency of your structure. And that's the expression of here. So that means if you are at resonance, which you can assume for many instances, simply because it is at resonance we'll see the largest amplitude, and at resonance we are particularly interested in the amount of damping because the amplitude is inversely proportional to the damping ratio. We will actually find that the loss factor is equal to 2 times the damping ratio. So there's a direct relation between the loss factor, the way we've defined the loss factor, and the damping ratio at the resonance frequency of our structure. So let's assume that we revert our solution for the loss factor so we can actually identify a viscous parameter. Because in many cases, you would obtain the loss factor from experiments, numerical solutions, knowledge of other damping mechanisms that you want to transform into a viscous parameter. So in many cases, you know the loss factor, and then you would like to obtain a corresponding or an equivalent viscous parameter, because that would allow you to use linear solution techniques like the frequency response function, such as time integration with linear systems. You'll have solutions for free damp vibrations where you can analyze the response of a structure, but it all depends on you obtaining a viscous coefficient. And it turns out you should take your loss factor, that's the one here, and multiply with the stiffness of the structure and the natural frequency, angular frequency by which you will then oscillate your structure. And in terms of the damping ratio, equivalent viscous damping ratio, if that is of interest, you should take half the loss factor and then the frequency ratio between the natural angular frequency of your structure and the applied angular frequency of your assumed harmonic motion. So this slide simply determines how to get from the loss factor to a viscous coefficient or the corresponding damping ratio, and they are both considered as equivalent because your real damping mechanism is not viscous, but it would behave in the same way as a viscous coefficient if you choose your viscous parameter so that it corresponds to the equivalent loss factor. Basically, it means that the amount of area inside the hysteresis loop should be the same for both damping models. Let's have a look at a fairly common source of energy dissipation. That's what we refer to as friction. Friction is not just friction, there are many types of friction. So we're going to consider the simplest idealized friction model, the so-called dry friction or Coulomb friction. So the idea is that we have a mass and we will slide that by a constant velocity, and above some threshold value we will have a constant restoring force that is independent of the amount or the magnitude of the velocity. So such a friction force is commonly decomposed into two things. We will have a friction coefficient and we will have some kind of compression force, here referred to as N. So for a block of material shown on this figure here, we will have friction at the interface between the block and the ground, and the normal force or the compression force is then equal to the weight of the block of our structure times the constant of gravity. But in principle, this mu n could be a single parameter. So you will mostly see mu n simply combined into a single parameter. Now the force-velocity relation, if we assume that we have harmonic velocity, is that when velocity is positive, we will have a force that operates in the opposite direction. So that means that for a positive velocity, we will have a negative force. And for negative velocity, we will have a constant positive force. And at the transition between positive and negative, we will somehow have a very fast transition between the two forcing values, idealized in this figure by an instant transition. In reality, you'll probably have some kind of smooth curve between the two regimes. We can put this on mathematical shape form because the friction force is then opposite, that means a minus, the force, and the force is mu times n, and we'll have a so-called sine function to take care of the switching. So for positive velocity, we'll have that the sine x dot is equal to 1, whereas for negative, we have that the sine function of velocity is equal to minus 1. And that secures the correct sign change between the two regimes, and in between we will assume a force 0, referring to this point here, but it doesn't really matter because in this model we have an instant transition between the negative regime and the positive regime. So we multiply our left hand side with minus x dot to get the energy dissipation, or the energy condition. So remember that x dot times Fd with a minus should always be positive, or always be non-negative. Now when we multiply with velocity on the right hand side, we will actually get a term that is equal to velocity times mu n minus, and we will then have a sine function with velocity. But remember, we should also change the sign, and that means I can remove this minus in front of my mu n. Then value times its sign is actually the corresponding absolute value. So we'll have mu n absolute value of velocity, and that is for positive mu n always non-negative. That means we have fulfilled our energy dissipation condition. And we can even substitute in our friction force into the left hand side of our equation of motion, where you will see that now we have a highly nonlinear term inside our equation of motion, representing the switching between positive and negative friction force and immediate switching associated with velocity equal to 0. If we have a look at this equation of motion and we divide by mass, we'll end up with an equation like this, where the g function is simply normal force divided by mass, and that is in our case mass times acceleration divided by mass, and therefore we will recover this acceleration coefficient, gravity coefficient here alongside the friction coefficient mu. Now let's assume that we start at some kind of initial displacement, and it is at rest, and that means when we release our structure with this initial condition, we will have a negative velocity associated with a reduction in the displacement. And that means that for the first part, this sine function here will be negative, and that means it can be removed or moved to the right hand side of the structure, so that for the first half period we will have to solve this equation. And that's an inhomogeneous second order ordinary differential equation with a solution that is given right here. So we have a term that depends on the initial displacement, and we have a term here that is coming from the particular solution to the inhomogeneous ordinary differential equation. And if we plot that, it actually turns out, as illustrated on the first figure here, that we start out from x0, and then we end up at the minimum point, where we will have a reduction in amplitude that is equal to 2 times mu n divided by the stiffness of the structure, k. So our friction mechanism dissipates energy, resulting in a reduction of the amplitude for this free vibration solution. Now, if we want to continue this, we would simply see that for the next part, velocity will not be negative, but positive. That means we're going to solve the same equation in 420, just with a minus in front of the inhomogeneous term, and that means we will have the same solution in the opposite direction, and we will actually again have the same reduction in amplitude. That means after the next half period, we'll not have 2 times mu n, we'll have 4 times mu n divided by k. We redo this again, and then we'll have 6 mu n divided by k, and by that we can continue. And this means that over a full period, we will have a reduction that is repeated for the next period, and for the next period. And as you can see, at some point, we will actually reach 0. So this was actually a phenomenon that we were not able to describe with pure viscous damping, because for pure viscous damping, the damping depends on an exponential function like this, and this is always larger than 0, so it never becomes 0. But the linear decrease in the peaks for friction damping actually allows our model to reach 0. The only thing is, of course, that at some point we have an internal force that is smaller than the locking force of the friction damper. So we have a criteria that the restoring force, that is x times the amplitude at a given maximum point, should always overcome the friction level. If it doesn't do so, we will simply have locking of the structure. So that terminates the vibrations, and we will mostly never lock our structure at an equilibrium point. That means exactly at 0. So we could, for instance, lock it here at a small offset compared to equilibrium. And this, or the number of periods that we can actually see before we see this locking, can then be estimated from this fairly simple solution, because we can estimate our amplitude, or the reduction amplitude, by these 4 mu n divided by k, and we can ask the question, when will we then simply meet our the threshold value for friction? And this will then be the number of amplitudes that we can expect before we actually have a full standstill of our structure. The hysteresis loop for friction is extremely easy to draw, because for positive velocity going from minimum to maximum, we'll have that mu n, or ff, is equal to minus mu n, but since we plot the negative damping force, we'll have a positive value in the hysteresis loop. And from the maximum down to the minimum, we'll have the same forcing amplitude, just with opposite sign. And that means we will run around in a rectangular hysteresis loop, like this. And then it's straightforward to calculate the area inside this loop, because we will have 2 times mu n times 2 times x. That's 4 mu n x. So in this case, we have an example where the dissipation of energy within a single period is most easily evaluated directly from the area inside or within the hysteresis loop, simply because the loop is so simple. So we take the energy, divide by 2 pi, and divide by 1/2 kx squared, and it turns out that we get an expression that is somewhat different than for the viscous damper, because in this case we do not get rid of the amplitude. That means our loss factor depends on the amplitude, and furthermore we see that we have a coefficient in here where the pi factor does not disappear. So we stick that into the expression for the viscous coefficient, which we remember is loss factor k divided by omega. So we take our loss factor, put in here. We'll see that the k's cancel, and we'll have an omega instead. So for a viscous, so if we have friction damping and we want to replace it by a viscous damper, we have 2 obvious problems. First of all, we should know the frequency at which the structure oscillates. That's fairly easy to overcome, because we, in most cases anyway, assume resonance. That means we know that omega is equal to omega 0. But the viscous coefficient becomes amplitude dependent. And this is kind of the hen and the egg problem, namely that the amplitude depends on the amount of damping, but in this case the amount of damping also depends on the amplitude. So it needs some kind of trial and error, iterative process to actually come up with a good guess for this viscous coefficient. But in many cases, it's not even possible to make, or it's time consuming to make simulations with pure friction. So if you want to have time histories, it's anyway a good idea to convert the analysis into a model with an equivalent viscous parameter. And we can find the corresponding damping ratio, where we can see that the frequency ratio will cancel for at resonance, and we get an expression that depends on amplitude. And it's in particular this amplitude dependence that makes the usage of an equivalent viscous damping parameter somewhat complicated. It's maybe worth noting that, as we've already mentioned, I'm just drawing a viscous elliptic loop, that of course the equivalent viscous parameter is the same as having the same area underneath the curve, of course assuming that we have the same amplitude. Now, if the area underneath the curve, or underneath the hysteresis curve, should be the same and x is the same, then of course the friction model should not reach the same damping value. So for the viscous coefficient we have larger maximum forces than we have for the friction damper, simply because we have parts that should even out to obtain the same area under or within the loops. So therefore, if you apply a viscous damping model that is equivalent to the same friction damper model, you will encounter a slight overshoot of the associated damping force, Fd. We have the issue with structural materials that our damping mechanism seems to be frequency independent. Now for viscous damping, we have that the force, that's c times velocity, is proportional to frequency. So if we increase the angular frequency, omega, let's say we double it, then we also double the amount of, or the magnitude of the forcing. But that is actually quite different in many structural materials, even steel, where we see a much smaller dependency on frequency. And that allows us, or suggests that we should, in the limiting case, maybe introduce a model that is totally frequency independent, so without any frequency dependence at all. So within this umbrella of frequency independent damping, we will typically refer to as hysteretic damping. So damping that does not change damping force, that does not change when we increase frequency. I made some experiments to indicate this. And a typical hysteretic damping model is seen in the figure to the left, where we start out the experiment at rest, and then we begin cycling the structural model in a constant loop, and we can see that we have different loops in here, and they change depending on some properties. Now, on the right-hand figure, it's actually investigated how this changes with respect to the cycling frequency. So in figure A, we have a small cycling frequency, 10 to the minus 2 hertz, whereas in B we reduce it even more, down to 10 to the minus 4. And what you see is that the two curves are basically the same. So although we change frequency, we do not change the overall behavior of the hysteresis loop, and the change in forcing amplitude is almost irrelevant. So that means for such a material, we actually have, or we need to look for damping models that do not depend on frequency, and therefore do not contain this omega inside the frequency magnitude of the damping force. For a linear viscous damper, V for viscous, we have a damping force that's equal to I c omega x. And remember that x dot is then I omega c x, when we assume that x is equal to some kind of amplitude, exponential function omega t. So that is our viscous force. However, if we want to get rid of this omega here, why not do the obvious and replace that by the frequency that we assume that our structure is oscillating at? For instance, the natural frequency, omega 0. And this is how we get hysteretic damping. The problem is that now we cannot transform our displacement back to velocity, because velocity requires an x and an I omega. But here, in this expression down here, we do not have an omega anymore. So therefore, we suddenly have a spring, because we retain our displacement x, and this spring will have an imaginary spring stiffness. And we will choose our c omega 0, we will refer to c omega 0 as bk. That means that our new damping parameter in this hysteresis model is equal to c omega 0 divided by k. Now, if we take this damping model and put into our equation of motion, you see the idea of introducing the beta function, because when you substitute this value or this expression here into our equation of motion, we can take the stiffness K outside a common parenthesis with the spring stiffness parameter, whereas the spring restoring force will give a unit value inside the parenthesis, and then our new damping parameter will have an I beta term as an addition to the spring stiffness. So therefore, hysteretic damping is associated with a complex stiffness parameter. This means that hysteretic damping is only applicable in a frequency response analysis. That means an analysis that is based on a frequency response function, estimation of a peak value divided by 2 zeta, whereas you cannot use the hysteretic model in time simulations, time integration solutions. So if you're using a commercial code and you want to apply hysteretic damping, it's also sometimes referred to as structural damping, you will simply not have the option to conduct a time simulation. All the analysis for hysteretic damping will stay inside the frequency domain, and you're in principle left to a frequency response analysis like the one we considered in lecture number 2. The loss factor for the beta parameter we obtain by simply substituting the viscous coefficient that we identify for this parameter into the expression for the loss factor, and we see that the beta parameter is equal to the loss factor at resonance. So it's fairly easily handled in a frequency response analysis, and it's commonly used to obtain the dynamic amplification factor for structures, but you cannot use it in a time simulation where you want to obtain the time histories for a response of a structure exposed to temporal loading from waves, wind, or whatever. So such a harmonic response analysis based on the frequency response solution is therefore worth considering. So we have the equation of motion, and we set this equation of motion with an external loading that is simply defined inside the frequency domain. Again, remember that F0 tilde is equal to the static displacement. That means that the complex amplitude is given by a frequency response solution, and we obtain that by introducing the complex solution into the acceleration term. That gives us an minus omega. So we will have minus omega squared plus 1 plus beta omega 0 squared, and then we'll have x equal to omega 0 f0 tilde. So when we identify capital X or isolate capital X, we'll need to divide by the parenthesis, and that is what we see in this expression here, where the omega 0 squared is appears in the numerator, while the parenthesis from the left hand side will appear as the denominator. So the frequency response function h can then be written as a complex stiffness relative to the inertia term. So we'll simply have an imaginary term that appears as hysteretic damping, and it comes from an imaginary stiffness component. So therefore, the damping term that we see here is actually frequency independent, simply because there's no omega in the internal forcing term that we see in the denominator of the frequency response function. If we think of equivalent viscous damping, we can simply compare this I beta omega squared with what would be in the same place in the frequency response function for the viscous damping case. And we see that this omega 0 cancels the other omega 0, and we can isolate the viscous damping ratio, which will then be like for the loss factor, it's beta half, and multiplied by the frequency ratio between the natural frequency of our structure and the loading frequency that we apply onto our structure. So for low frequency behavior, we actually come up with a hysteretic damping ratio that is larger, because this ratio here becomes larger than unity, and conversely it becomes smaller when we oscillate it at higher frequency. Of course, compared to the viscous damping case. The final case we will here refer to as fluid damping. It is associated with a stream of material around basically a structure, but in most cases the analysis is most appropriate for a cylinder, but the coefficient of our damping model depends very much on the geometry of the body that the flow is streaming around. So the idea is that we have some kind of flow approaching our structure, and we'll have a stagnation point where the structure or the flow will split around our element, and the behavior is then proportional to velocity, because you will simply force the structure, assume that the structure is forced through the fluid material, and that will allow us with a fluid force in the opposite direction. And it turns out that the force-velocity diagram will be non-linear. We will have a zero value and zero inclination at zero velocity, and then we'll have an increase of the force towards the maximum amplitude at omega capital X. And a fluid force that provides such a behavior can be written as a coefficient alpha times velocity times absolute value of velocity. And if we remember that the absolute value of velocity is equal to the velocity times its sign, we can alternatively write the fluid damper force as alpha x squared, dot squared, times the velocity of x dot. Now, remember that F fluid, the damper force, is expressed with a minus inside in the hysteresis representation. That means that without the minus, it appears as an internal force that can be placed on the left-hand side of our equation of motion. That means we have inertia, stiffness, and in between we have this non-linear fluid drag force that dissipates energy. Let's have a look at the energy dissipation condition. So we need that minus F fluid times x dot is non-negative. So that means we have alpha x dot absolute value of x times x dot. That gives us alpha x dot squared absolute value of x dot. And this is non-negative, of course, alpha larger or equal to 0. So therefore, we have, by this, we have fulfilled our dissipation condition. In fact, you can generalize this fluid model into a so-called power law model. When you add the power, in this case gamma minus 1, to the absolute term. Thus, if you have gamma equal to 0, you will actually obtain what we refer to as friction. If you have gamma equal to 1, then you'll have pure viscous damping, and if you set gamma equal to 2, you will actually get the fluid damping that we have on this slide. So if you want to introduce a fairly general damping model into your dynamic system, try to consider the so-called power law model, because it's very versatile and it can capture a lot of different damping mechanisms. Of course, it's non-linear. It has two parameters instead of one. It has an alpha and a gamma. So of course, the analysis will also become more complex. We could consider finding the loss factor and setting up the conditions for equivalent viscous damping in the same way as we have done for instance, the friction damper. But let's try a slightly different approach that is related to the loss factor, and it's based on so-called harmonic averaging. So we have a fluid force model that is equal to minus alpha x dot and then times the absolute value of velocity x dot. And what we're going to do initially is to assume harmonic displacement by cosine, and that means that the velocity will be a sine function. Then we're going to eliminate the fluid damper force by a viscous damping coefficient. And that means we will have a relation where we get rid of the fluid damper force. So let's just write that here. So we will have C and then equivalent x dot equal to minus alpha x dot. And I'm pretty sure there's supposed to be a minus in front of here. What we'll do now is that we will then substitute in our harmonic velocity, and that means we will get C equivalent, and then we'll have a minus from the velocity cancelling with the minus in front of the C equivalent. And that means we'll have omega capital X sine omega t equal to minus, and then we will have a alpha, and then we'll have minus omega capital sine omega t, and then we'll have the absolute value of omega capital X sine omega t. There's a minus in front inside the absolute sign. So the two minuses on the right hand side will cancel. That means you will have alpha omega capital X, and in fact we'll have a omega x squared, because we also have an omega x from inside the absolute sign. Then we'll have a sinus omega t and an absolute value of sine omega t. Suddenly we have a relation that involves an equivalent viscous parameter on the left hand side and a right hand side that depends on our fluid damper parameter, that is alpha. We would like to get rid of the temporal dependence, means the sine functions. So we will do that in terms of dissipation of energy, and that means we multiply both sides with velocity and then we integrate over a period. Now this involves a period on the left hand side that becomes equal to C equivalent. Then we multiply by omega capital X, that means we have omega capital X squared. Then we have an integral over the period, and inside we have a sine function squared omega t dt. On the right hand side we will have an alpha, then we'll have omega capital X to the power 3, because velocity provides omega x. Then we'll have an integral 2 pi divided by omega. Then we'll have a sine function squared multiplied by the absolute value of a sine function dt. And this is actually the expression that you see in 433. So this procedure, this 4-step procedure, will give you this expression here. And what you're looking for, what we are looking for, is the equivalent viscous damping parameter. First of all, we see these two cancel and eliminates the power of 3, reduces that to the power of 1. So everything boils actually down to solving these integrals. Now the latter integral we have already solved previously, because again we multiply by omega, and that means we should also divide by omega, and then the limits change from 0 to 2 pi, so we get rid of this omega here, and this integral is actually pi, and that means that the right integral in 433 is equal to pi divided by omega. Now the other integral on the left hand side becomes a little bit more complicated. But let's just try to plot, as indicated here, a sine function. Or let's plot the absolute value of a sine function. So for the first half period, the absolute value of a sine function is actually equal to the sine function itself. And we want to integrate over a full period. But the next half, the area, the behavior of the sine function will be the same as for the first half. So therefore, instead of integrating over a full period, you can multiply by 2 and integrate over the first half. And for the first half, the absolute value of the sine will be a sine that can then combine with the two other sine functions to give sine to the power of 3. Again, we multiply by omega, remember to divide by omega, and then you evaluate this integral. And it turns out that this integral will give you 4 over 3. look up into a mathematical table, use a computational tool, do it numerically, and that means that the other integral will be 8 over 3 omega. So this one goes into the left hand side, whereas this one will go into the right hand side of 433. And this will provide us with this extremely simple expression for the equivalent viscous coefficient for a fluid damper model considered in this problem here. And we can transform that into a damping ratio. Again, we see that the frequency dependence disappears when we are at resonance. But what is different from the friction model is that we actually have proportionality with velocity. If you go back to the friction model, your capital X would be in the denominator. Now it's actually in the numerator. So we have frequency dependency, yes, but we will have proportionality with capital X. That's the amplitude. So that's a generally different behavior than for friction. So when we consider friction, we will have a viscous coefficient that is inversely proportional to X. We'll have a fluid damper model that is proportional to X, and we'll have a hysteretic damping model that is independent of frequency omega. So these are the three typical models that you will encounter in structural dynamics. Let's at the end have some typical damping values, and we are going to consider the damping ratio. Always be careful to distinguish between the damping ratio and, of course, the loss factor. And to make matters worse, we actually also sometimes represent damping by the logarithmic decrement. So there are many measures that can be used to express damping, and I've too many times seen a loss in translation between professionals discussing damping, not really considering, for instance, the 2 pi factor between the logarithmic decrement and the viscous parameter, or the 1/2 that appears between the damping ratio and the loss factor at resonance. So guidelines here will be in terms of the damping ratio. So for instance, for modern type structures, we could have steel, pre-stressed reinforced concrete, a combination. We are at a minimum where we are at a per mil, and a maximum where we are at a few percent. Somewhere in between there. For lightly damped structures, such as chimneys, towers, masts, please see that the reference here is fairly old, but still, we are at a lower end where we are down to a few per mil, whereas the maximum can be for a few percent. So we could go, roughly speaking, from 0.5% to 5%, where this could be even lower, and this is probably to the high end, at least for modern structures. The damping ratio also depends very much on the type of excitation you put to your structure, because as we've seen, the damping ratio, the equivalent damping ratio, depends on amplitude if you have a nonlinear damping model. So in case of earthquakes, you will have a very large, strong, violent excitation of your structure, and that means you will actually have larger deformations that could result in larger apparent or equivalent viscous damping parameters. So when you are beyond yielding, you will have the order of magnitude that we discussed previously, but once you approach the yielding point, you will of course dissipate much more energy, because yielding is associated with material damage, and that is energy that simply disappears out of the structure, and suddenly you have totally different levels of damping ratios. But again, one could argue that for an earthquake with impact loading, the amount of damping is not really that crucial for the maximum deflection. It's governed by the stiffness of the structure. So often these large damping values will not save your structure from destruction. I'll leave the summary to you, but remember that the dissipation condition should always identify your damping mechanism as being non-negative. You will have a loss factor that represents the link between your nonlinear damping mechanism and viscous damping by this relation to the equivalent viscous damping ratio. Could have different damping models, friction, hysteretic, fluid damping, and in most cases it's actually quite difficult to estimate the damping. So that is actually an ongoing research area where we hopefully within the next decade will make some huge advances and be much better at estimating the damping in real life structures.